Hey y'all, this is kind of a test trial for me to see if you can hear my audio when I'm wearing headphones. So I hope you can. This is video 1.9.2, where I'm trying to give another example of when is it going to be best to use analytical, tabular, and a graphical approach to trying to find a limit. So I'm going to start by sharing these whiteboard screens. So here's my video, which approach works best. And I wanted to break down initially some pros and cons to each approach, because as you've probably learned by now, there's not a clear answer, and it depends on the limit you're being asked to find about which approach is going to work best. So when we say analytical, we really mean algebraic, like trying to use our plugging in, our rationalizing, our factoring, our trig identities to try to find a limit. Pro of this method is it's precise. If we can analytically find the limit, we're going to have the exact value. The drawbacks or the cons is that it's tedious. It can take a lot of time. And at times it's actually not possible to do. So we can actually dig ourselves really deep into these rabbit holes of trying to find the limit by hand, and it's not possible. Other one is using a table of values. Benefit, it's also precise. Drawback is it's also tedious, and at times it can be misleading. Like if you're dealing with an oscillating discontinuity, your table of values might show that your function values, your y values, your f of x values are jumping around, and it could make you draw an erroneous conclusion that the limit is approaching a certain value when really it's not. And the last one is using a graph. Benefit is it's quick. Drawback is it has limitations. Like I think you all probably by now are like, yeah, if I have a graph, it's really easy to find the limit, and you're right. If I have a graph of a function, I can figure out that y value. It's going to be the easiest, quickest method. But at times it might just not be as precise as you want to be, and we can't always use that approach. So I'm going to kind of detail 3 examples that kind of show off the benefits of using a certain approach in a certain situation. So right here I have the function f of x is equal to x cubed minus 2x squared minus x plus 2, all divided by x squared minus 4. And I'm curious to know, what is the limit of this function as x approaches 2? Well, if we plug in, and trust me on this, you can also do it, we end up with indeterminate form, which just tells us that we don't know for sure what the limit is. So now we have to go into our bag of tricks to figure out what is this limit. Now I noticed that these first 2 terms have x squared in common, so I'm going to try to factor. I'm going to try to rewrite this function by factoring. So I'm going to take an x squared out of the first 2 terms, which is going to leave us with x minus 2. Then I noticed that that's almost really close to the last 2 terms. So if I factor out a -1 from the last 2 terms, I have a situation where I can factor by grouping. So now I'm just going to regroup that x squared, those 2 x squared terms together. So now we have this function, f of x is equal to x squared minus 1. And I could factor that if I want to. I'm not going to in this case because it's not necessary to cancel anything. But x squared minus 1, and then times x minus 2. And then this denominator is the difference of squares. So I'm going to factor it into x minus 2 and x plus 2, which is really nice because now that cancels. And so I'm left with this function that is x squared minus 1 divided by x plus 2. Now, to be clear, if I'm redefining this function, I'm saying these are equivalent. I do have to say that this function works for when x is not equal to 2. What I've done is this function right here with this sort of piecewise setup. And I guess that when x is equal to 2, the function is undefined. So we'd say undefined when x equals 2. This will act like the original function. It's not the exact original function because the original function has a discontinuity there, which you'll see in a second. But approaching this analytically, I can now actually evaluate this limit at that value because I've gotten it out of indeterminate form. And so now when I do direct substitution, although the value is not going to be defined at that point at x equals 2, I can still figure out where the function is approaching. And so if I plug in x squared is 4, minus 1 is 3, and then 2 plus 2 on the bottom is 3/4. So this limit is going to be equal to 3/4. I'm going to stop sharing and share my Desmo screen. So here's a look at this function right here. So here's the original function. If I start to move my mouse along it, we can kind of take a guess that as I'm getting closer to x equals 2, it looks like I'm getting close to 0.73 something. And now we know the limit is 0.75 or 3/4. But if I had just used a graph, it wasn't going to be clear what the exact limit was, and I would have been guessing. This is the function we created by canceling out the x minus 2 factors. And again, if I go along this function and I get to that value, it's defined at that point because of how I've changed the function. But if I was going to write it as the equivalent value, I would say, it can't equal x equals 2 so that they are a direct representation of each other. But now that I have rationalized it, now that I have factored and canceled and removed that discontinuity, which still exists in the original function, like this function still has a discontinuity there. Our function, once we canceled, doesn't act like that, which allows us to directly plug in, but it is still just a representation of the original function. Point being that if you had just used the graph, it might have led you astray, but if by using our analytical approach, we got the exact value. And a table would have worked well, but I think it might have been more tedious than the work we did. You could disagree and use a table and you would have done just fine. So now second up method is, okay, when's it going to be appropriate to use a table? Well, right here we have this absolute value function. And whenever you see absolute value functions where you have the same expression sort of top and bottom, or really just absolute value functions, that should be a big light bulb saying I should probably use a table approach. There's no algebraic trick I have to like rationalize an absolute value function. And using a graph is going to be the easiest, but you're not always given that option. So I want to show how we can still get this answer if I want to know the limit as x approaches 4 of this function just by using a table of values. So I want to start by picking values that are close to 4 and getting approaching that value. So I'm going to try 3. I'm curious about 3.5 and then 3.9 and then also 3.99. Now we know when we actually plug in 4, that value is undefined. You would be in indeterminate form then, which doesn't tell us if the limit's possible or not, just like it's undefined at that point. And then we'd also want to test out 4.01, 4.1, 4.5, and then 5. We probably could do without 3 and 5. I think most people skip right to like 4.5 or even 4.1. But this is essentially evaluating what is the limit of this function as we approach from the right side of g of x, and then what is the limit of this function as we approach from the left side of the function g of x as that function is approaching the value of 4. And we're curious, do they have the same value? If they do, the limit exists at that value. If they have different values, the limit of this function does not exist for when x is approaching 4. So when I plug in 3, if I plug into this function right here, I just have 3 minus 4, which is -1. And then 3 minus 4 is -1, and the absolute value makes that a positive value. So -1 divided by 1 is -1. I'm going to erase and plug in now 3.5. That would be -0.5. And then 3.5 minus 4 is also -0.5, and the absolute value bars make it positive. So you might start noticing, oh, like I'm always dividing by the exact same value, just the numerator is going to be negative because all of our values less than 4 are going to make the numerator negative. So all these values are going to be -1 leading up to 4. And then you might have already been ahead of me and figured out the right side. I'll just plug in 2. If I have 4.01 minus 4, that's 0.01. And then 4.01 minus 4 is also 0.01. The absolute value just keeps it positive. So now we're actually dividing by the exact same value. If I plug in 4.1 in for x, I get 0.1, and then I also get 0.1 in the denominator because I have all positive values as all these values are greater than 4, so subtracting by 4 is still going to leave us with positive values. So we have all these positive values, so the limit as we approach from the left side is -1. The limit as we approach from the right side is +1. So we'd say that this limit, I'll put it up here, we'd say does not exist. In shorthand, we can write DNE for does not exist. If I share my screen here, this one would have been way easier just looking at the graph, but we don't always get that privilege of looking at a graph on a test or on the AP test. Notice how Desmos has a really cool absolute value feature. So if you just put ABS, it actually graphs the absolute value. We can see this function right here has a pretty clear jump discontinuity where x equals 4. Notice if I had asked the question, and I can annotate on the screen because Zoom is cool. If I'd asked the question for the exact same function, what's the limit as x approaches 3 of g of x? That's pretty easy to do. As I approach 3, which is that point right there, the limit's just -1. It's only as I approach right at x equals 4 that this function does not have a defined limit. Every place else it has a defined limit. It's going to be -1 for all values less than 4 and +1 for all values greater than 4. But right at that value, you have a jump discontinuity, so the limit does not exist there. I'm going to erase this, and then I'm on to my very last point. And I hope you can hear me, otherwise I'm going to be very sad. So these two are examples of where, okay, if I plug in, I don't get indeterminate form. I get where I have a numerator over a 0 value for both of these, which gives me a hint that I probably have a discontinuity there, so the limit probably does not exist. Doing a table would work here, but it might be more tedious. And so this is really a great time where if we have a graph's going to give us a lot of information. It's actually going to be a little surprising for the second one. So if I share off this one right here, I can pretty clearly see as x approaches 2, as I approach, as the limits, that's a big arrow, as x approaches 2, I'm going to say from the left side of h of x, it looks like we're going off to -infinity, but as we approach 2 from the right side, just larger values than 2, and think about that number line. It looks like I'm approaching looks like +infinity. These limits don't match, so like this limit right here, we'd say does not exist. The left and right side of limits don't match, the limit does not exist. What's really interesting though, I'm gonna exit out here and actually let me erase. What's really interesting is for this function, it might be quick to say if I am trying to figure out the limit as x approaches 0 of this function j of x, looking at the graph, you might say, oh, it's the limit does not exist. But notice how the left and right sided limit are both, I'm going to see if I can zoom out a bit. I'm just going to mess with where I wrote, it's fine. Notice how the left and right sided limit both seem to be approaching +infinity. So we actually could say, you could say unbounded, which is what Khan Academy uses, that language. But I could also say, because the left and right sided limit both approach the same like infinite value, I could say this limit does exist, which is kind of weird saying it approaches infinity, because the left and right sided limits do eventually reach the exact same value. So I hope this was helpful. As always, if you have questions, let me know, and I'll see you soon.